Okay, so welcome to this next video in which we are discussing the construction of the field of fractions from an integral domain. Okay, so we have now shown that the addition operation that we've defined on this set of equivalence classes does indeed form an abelian group. What we now want to show is that the multiplication operation that we've defined, firstly that it has a multiplicative identity, secondly that it obeys associativity, thirdly that all non-zero elements have an inverse, okay, and finally that it's commutative. We then finally want to end by showing distributivity, and then what I just want to make a comment on is how this bigger structure that we've created does in fact contain the initial integral domain. So what we have effectively done is constructed a bigger structure which contains our initial integral domain and all of the addition and multiplication on that, but is bigger and then is a field. Okay, so let's then we'll begin by showing that we have a multiplicative identity. Right, so remember what we have done to draw our trusty picture here is we have created this set of fractions, okay? We've then divided it up into equivalence classes, and we have defined addition and multiplication laws on these equivalence classes. We now want to show that there is some equivalence class which we'll call, let's say, the one equivalence class, which is going to be the multiplicative identity, okay? And basically, if you take any other equivalence class, let's say alpha down here, and you multiply alpha by 1 either on the right or on the left, okay, this is just going to give the alpha equivalence class back again. Right, so how do we multiply two equivalence classes firstly? Well, if you have alpha times another equivalence class, let's say beta, the way that you multiply them is you take a representative from the equivalence class alpha, you take a representative from the equivalence class beta, let's say the representative from alpha is A over B, okay, and let's say the representative from beta is C over D, and you combine the two together. That's all that symbol there means, combine the two together to make a new fraction which is AC over BD. Okay, this is a fraction. It will be in some equivalence class, maybe up here, and that equivalence class which contains this new fraction is then the answer to what the alpha times beta equivalence class is. Okay, right, so we now want to prove that there is some equivalence class 1, which we're going to call 1, where no matter which representative of the alpha equivalence class you pick, and no matter which representative of the 1 equivalence class you pick, when you combine these two fractions together, you'll always get another fraction which is within the alpha equivalence class. Okay, now this 1 equivalence class, I claim this is the equivalence class that contains all things of the form A over A, okay, where A is any element of the domain except 0, so A is not equal to 0, because clearly we can't have 0 in the denominator. So this is the equivalence class that contains 1 over 1, 2 over 2, 3 over 3, if you're in the integers, of course. If we're in a general integral domain, then of course it's different. But basically it contains all things of the form A over A, basically. And these are all equivalent, basically, to a single element that is really important that is within here, which is 1 over 1. So all integral domains will have a multiplicative identity. So this symbol here is now the multiplicative identity in this original domain. Okay, so this fraction that is made by the multiplicative identity over the multiplicative identity, this will be in this identity equivalence class, this multiplicative identity equivalence class, okay? And then all other things of this form will also be in that equivalence class. The reason is that these are going to be related to one another because they satisfy the condition, because this one times this one, 1 times A, is going to be equal to this one times this one, 1 times A, because obviously both sides are just equal to A, so it's true. Okay, right. So that's what this equivalence class is going to contain, but the important thing is that it contains this crucial element here. And this is the element we will use we'll use this as our representative, basically, of this identity equivalence class. Why wouldn't we, basically? Why would we use some more difficult representative when we can just use this? This is the ultimate representative of this equivalence class. It's the easiest one to use. And then we use the fact that we've already done all that hard work in showing that multiplication was well defined to say that it would have given you the same answer whether you'd picked any of the representatives. So we don't need to redo that work, basically. So let's take any old equivalence class alpha, take a representative, and let's take the multiplicative identity, or what I claim is the multiplicative identity equivalence class, and multiply it by alpha. Well, the way we do this is we take a representative from the multiplicative identity equivalence class, and we're going to pick this ultimate representative here, and we combine it with our generic representative of this alpha equivalence class to get 1 times alpha over 1 times beta, which is just a over b. Sorry, 1 times a over 1 times b. I apologise for saying 1 times alpha over 1 times beta. 1 times a over 1 times b, which is just a over b. And clearly that's in the same equivalence class. So if you used a different representative from this multiplicative identity equivalence class, what it would do is it would change the fraction we were talking about. So when you combined it with a generic representative from alpha, it would give you a different fraction in this same alpha equivalence class. Okay? But by using this beautiful representative of the multiplicative identity equivalence class, we can, when we combine it, it doesn't even change the fraction, which is just perfect. Okay, and of course this works the same if you do it the other way around. So if you take alpha times 1 instead, then, and that should have been a alpha times 1 there, not an alpha equals 1. So if we do alpha times 1 instead, well, this is going to be the equivalence class that contains a over b times 1 over 1, which is again just a over b, so clearly the answer again is just alpha. So the multiplicative identity is the equivalence class with 1 over 1 in, basically. So again, we have a multiplicative identity. So, first property is shown, we have a multiplicative identity. Okay, now what we want to show is multiplicative associativity. Okay, so the next property is associativity. Right, so we need to show that if you take the alpha equivalence class, multiply it by the beta equivalence class, okay, you'll get another equivalence class, and then you multiply this by the gamma equivalence class. We need to show that that's the same as if you take the alpha equivalence class and multiply it by what the beta times the gamma equivalence class is. So let's draw some pictures here again. It always helps to draw pictures. Okay, so here is our set of fractions here. And we have partitioned up our set of fractions into equivalence classes, like so. Okay, so here are the equivalence classes. Right, and then we've got these 3 equivalence classes. We've got alpha, beta, and gamma, which I'll put all together here. Okay, right, so here is alpha in red, here is beta in turquoise, and here is gamma in turquoise. Whoops. Okay, so there's alpha times beta times gamma. Now, we're going to multiply alpha times beta. So we're going to take a representative of alpha, which we'll call a over b. We're going to take a representative of beta, which we'll call c over d. We're going to combine those together by multiplication to get a fraction a times c over b times d, which is in some equivalence class that we will then call alpha times beta. Okay, down here. So in orange, this is ooh, that's smudged horribly, never mind. That's the alpha times beta equivalence class. Now, what we'll then do is combine this fraction with a fraction from gamma, which we'll call e over f, okay, to get a final thing, which will be a times c times f over b times d. Oh dear, what have I done? No, that should be a times c times e over b times d times f, basically. So we've combined this fraction then with this fraction, okay? So we're multiplying now this equivalence class with this, and all we need to do for that is take a representative of this equivalence class, and we might as well pick the representative we've already found, rather than saying use some different representative, okay? And then we're going to multiply it with this one here, combine it with this one to get this fraction, and this will be in some final equivalence class, which is down here, which is alpha times beta times gamma. Alternatively, what you could do is you could multiply beta and gamma together, okay, so combine those two fractions here to get some fraction c times e over d times f, which we would call the equivalence class beta times gamma. Okay, so here it is, which has this representative c times e over d times f, and then we'd take the alpha equivalence class, take a representative there, combine it with this representative that we found already from this equivalence class. And in principle, you could take any other representative, but why would you? Why would you not use the representative that we've already found? So we take this representative, combine it with this representative, and we get something else. And we want to prove that that is at least in the same equivalence class as this one, i.e. that the answer to alpha times beta times gamma is the same as alpha times beta times gamma. So they at least need to be in the same equivalence class. In reality, they're going to actually give the same fraction, because if we combine, let's say, the alpha one up here, if we take a over b and we combine that with ce over df, then that's going to give us a times ce over b times df. Okay, and we can just say that that's the same as that because of associativity in the integral domain, because of multiplicative associativity in the integral domain, because a times c times e here is the same as ac times e in the integral domain, and on the bottom, b times d times f is the same as bd times f in the integral domain. So multiplicative associativity in the integral domain gives us multiplicative associativity in our set of equivalence classes, basically. Okay, so we've got that one now. Now the biggie. We want to prove multiplicative inverses for all elements apart from the additive identity. Okay, right. So we want to prove that if you take any equivalence class, alpha, let's say, within our set of equivalence classes here. So here is our set of fractions partitioned up into these equivalence classes. And we want to prove that if we take any equivalence class alpha, that there is some other equivalence class which we'll call alpha to the negative 1. Okay, so the multiplicative inverse of alpha. Okay, so here in pink is the multiplicative inverse of alpha. And here in blue is alpha itself. We want to prove that there always exists another equivalence class, alpha to the negative 1, such that if you combine these two together, if you multiply the two together, it's going to give us the identity equivalence class. Okay, right. So, I don't think... it should be pretty intuitive what we're going to do. Okay, so... if you have this alpha equivalence class, let's say that the generic member of the alpha equivalence class is a over b, where a is an element of the domain and b is an element of the domain except 0. Okay, right. And basically, you're then going to go to the equivalence class which contains the element b over a. Okay, and this is why you can't do it if this is the additive identity equivalence class, because if this is the additive identity equivalence class, then you have 0 in the numerator, basically, and then whatever you want in the denominator, and then when you turn it upside down, you'll have 0 in the denominator, which no fractions within this set has, because all of them have a non-zero denominator. So basically, you can't do this for the 0 equivalence class, but you can do it for all others. Okay, because all others have a non-zero numerator. The 0 or identity, additive identity equivalence class contains all the elements with 0 in the numerator. Okay, but so for all other equivalence classes, you can do this. You can construct this fraction for this. Okay, And now you can go to whichever equivalence class has this fraction in. And my claim now is that this other equivalence class, which has this other fraction in, where we've swapped the numerator and the denominator, will be the inverse of this equivalence class. Okay, and the reason is that if we want to multiply these two together, all we need to do is find two representatives to multiply together. Well, why don't we pick these two representatives we already know? Okay, so combine these two representatives together, and what do you get? You get a times b over b times a. Well, swap that around. This is a times b over a times b, and of course we know that all things of the form a over a are within the multiplicative identity equivalence class. Therefore, this is all in the multiplicative identity equivalence class. And therefore, we have found an equivalence class that multiplies together with this alpha equivalence class to give the identity equivalence class here. Because, of course, the answer then to this multiplication of alpha times alpha inverse is that it's the equivalence class containing this, and that is the identity equivalence class, the multiplicative identity equivalence class. Okay, so there's the inverse of all non-zero elements. Now, what we need to prove is commutativity. Okay, so next up is commutativity. So we need to prove that alpha times beta is equal to beta times alpha. So alpha times beta needs to equal beta times alpha. Well, again, just pick representatives of your alpha and your beta equivalence classes. So let's say beta is down here, and beta has some representative c times d. Okay, so the answer to alpha times beta is just to find the equivalence class which contains the combination of a over b and c over d, which is ac over bd. So you'll find the equivalence class with this in. And beta times alpha, the answer to that is find the equivalence class which contains the combination of c over d with a over b, which is ca over db. And of course then we can just apply commutativity of multiplication in the integral domain to say that this is the same thing as ac over bd. So in fact you're bound to get the same equivalence class, because actually if you use the same representatives, the fraction that you're going to end up with is exactly the same no matter which way you do it, basically. So you're always therefore going to end up in the same overall equivalence class. So this is always going to be the same answer, basically. Okay, so we have multiplicative commutativity. Now, the final biggie, which is distributivity. Okay, right, so let's explain what we need to do. So again, a picture will help. Right, so here is the set of all fractions. We've divided it up into equivalence classes. And now, we don't need to show both right distributivity and left distributivity because we've got commutativity. So if you've got one of the distributivities and commutativity, you'll have the other two. So all we need to show is that if you take alpha and multiply it by beta plus gamma, that this is the same thing as taking alpha, multiplying it by beta, and then adding that to alpha multiplied by gamma. Okay, so what does this mean? Well, as usual, let's draw our three equivalence classes on. So let's let this green one be alpha here. Okay. Let's let this orange one here be beta. Okay, so this is beta. And let's let this pink one here be gamma. Okay, right. So, what we need is representatives from them all. Okay, so we'll say that the representative from alpha we're going to use is a over b. The representative from beta we'll use is c over d. And the representative from gamma we'll use is e over f. Okay, so on this side, what we need to do is we need to combine beta and gamma together, okay, and get some other equivalence class. So we need to work out what is beta plus gamma. Okay, so we know how to do this. We take the representative of beta, we take our representative of gamma, we combine these two together to get a new fraction, which is cf plus de over df, like so. And this fraction, this new fraction, will be in some final equivalence class, which we'll call beta plus gamma here. Okay, so let's colour that equivalence class in turquoise. Okay, and then we need to multiply this equivalence class, beta plus gamma, by alpha. So we need to multiply alpha times beta plus gamma. And the way we would do this is we take a representative from alpha and a representative from beta plus gamma, and we might as well use this representative here. It would be very sensible, okay? And we're going to combine them together. So we'll take our A over B, and we'll combine it with CF, and this is where we need to be strict with our brackets, plus DE over DF. Okay, so now combine them together, and what we'll get is A times CF plus A times DE. So I've applied distributivity here. I've said that A times all of this is the same thing as A times this one and A times this one, because distributivity clearly works in the integral domain. Okay, over B times DF. Okay, so that's the answer we get by doing this. Now we're going to see what answer we get by doing this, and we need to prove that whatever fraction you get by doing this, at least it's in the same equivalence class as this. Okay, it may well be the same thing, but we at least need to prove that it's in the same equivalence class. Okay, so we finally ended up with some final equivalence class, which I'll colour in blue, maybe at the top here, which is alpha times beta plus gamma. Okay, this time we'll multiply alpha and beta together, okay, to get some equivalence class which we'll call alpha times beta, okay, and to do this what we need to do is take two representatives, combine them together, so A over B, and we need to times it by C over D, so combine them together to get some new fraction AC over BD, and then the answer to alpha times beta is whichever equivalence class contains this. So this equivalence class here, which is alpha times beta, has this as a representative basically. Then we'll also do alpha times gamma, okay, we'll say that this one is this one down here, alpha times gamma here, and again the way we do this is we take our representative from alpha, we combine it with our representative from gamma, which is E over F, which is AE over BF, and then the answer is whichever equivalence class then contains this representative basically. Okay, and then what we need to do is take our representative from here, or at least a representative from here, and add it to a representative from here, okay, and we might as well use the representatives that we know. So what we're going to do is combine this representative, AC over BD, with this representative, which is AE over BF. Okay, and this will give AC, okay, and we need to be strict with our brackets, times BF plus, and then on this side, BD over times AE over BD times BF. And now what we need to prove is that these two are related to each other. So we need to prove that we've ended up in the same equivalence class. So we need to prove that this is also in this blue equivalence class up here, that we've just ended up with two separate things, that this here is one of these, and that this here is another one. Now what was the condition to be in an equivalence class? Well, basically I had to be able to multiply this by this, and this by this, and they had to give the same thing. So we need to see whether the numerator of this one, which is A times CF plus A times DE, times by our denominator down here, which is BD BF, is equal to the denominator here, which is B times DF, okay, times the numerator here, which is AC times BF plus BD times AE. Okay, have I done that right? So we've taken the numerator here, multiplied it by the denominator here, multiplied it by the numerator here, and we want those two to be equivalent. Okay, well, we want them to be equal, we want them to be more than equivalent, and that will show that these two are in the same equivalence class. Okay, so really there's nothing to do except multiply out. So we'll get, this is A times CF times, then we'll have BD, okay, and strictly speaking we should have a bigger brackets around here, but I think we can do away with that, times BF plus A times DE times BD times BF, and that's going to be equal to B times DF times AC times BF on here plus B times DF times BD times AE. Now, painstakingly you could go through all of the associativity. We won't quite go that far, but we'll acknowledge that both sides are hopefully the same. Right, if I've done this right, so which one shall I guess is equal to which one? Well, this one doesn't contain an E, so it can't be the same as this, so it must be the same as this. So let's hope and pray that both sides stack up. So there are two B's, there are two B's here. Okay, here is a D, there's a D here. Okay, here is an F, and here is an F. And that colour doesn't look any distinguishable from that. Here is an F and here is an F. And when you put them next to each other, maybe you can see the slight colour difference there. Here is an A, here is an A, and then finally there's a C. So here's the C, and here's the C, finally. So those two sides stack up, and again, this should hopefully stack up. So you've got one A, how many D's? Two D's, 1, 2, and E, which is here. A, two B's, 1, 2, another D which we've already done, and an F here. So yes, those two sides stack up as well. So yes, they are related to one another. They're in the same equivalence class. So again, distributivity holds. So this structure that we have created, it is a field with P. But what does it have to do with the original integral domain? Because this was the crux of it. What we were trying to do was extend our initial integral domain into a bigger structure, which was then a field. This feels like we've constructed some horrendously abstract thing that has nothing to do with our original integral domain, but it does, basically, because in our new structure, in this set of equivalence classes of the set of fractions, okay, there are a bunch of equivalence classes, okay, which are equivalent to the members of the integral domain. Okay, so if we have the initial integral domain here, so let's say this is the set containing all of the elements of the domain, okay, then basically for every single one of them there will be an equivalence class that effectively represents it. So for instance, for the additive identity, the 0 equivalence class, this is everything with 0 in the numerator. This is effectively matched to the 0 member here, basically. Okay, so how do we take a generic element in the domain and find the equivalence class that matches it? Well, basically, it will be the equivalence class that has A over 1, where 1 is the multiplicative identity of the domain in. So for every element in this domain, you can find an equivalence class that contains the fraction A over 1. And my claim is that that equivalence class, basically, it's the representative of this structure in this larger structure, basically. And let me try and explain that a little bit more. Okay, so every single element in the domain will have one of these equivalence classes, and it will have its own distinct equivalence class. Okay, so let me prove that. Let me prove that A over 1 will not be related to B over 1. So if you take two elements in the domain, A and B, so we'll keep them nice and general, my claim is that they will be in separate equivalence classes. A over 1 will not be related to B over 1. So every single one of these fractions where you take an element of the domain and put it over the multiplicative identity will be in a separate equivalence class, is my claim. And the reason, quite simply, is that if these two were related, then it would be true that A times 1 was equal to 1 times B, which can't be true because that would claim that A was equal to B, which isn't true in this integral domain. A and B are distinct elements. Okay, so every element of the integral domain has its own equivalence class. Has an equivalence class with this fraction, which is A over 1 in it, basically. Okay, now, when you add any two of these together, so if you take A over 1 and you add it to B over 1, so if you take this equivalence class which contains A over 1 and you add it to this equivalence class that contains B over 1, then we might as well use these two key representatives, and I should state that they will have other members within them, okay, but we'll use these two key representatives, and I might even call this equivalence class A, and I might call this equivalence class B, because they are effectively these initial elements in the new structure that we've created, basically. Okay, so if we want to add A to B, then we'll have to take two representatives and combine those together. But how do we do this? Well, we take this one, multiply it by this one, and then take 1 and multiply it by B, and then put it over 1 times 1. But A times 1 is just A, B times 1 is just B, okay, and 1 times 1 is just 1. So A over 1 plus B over 1 is equal to A plus B over 1, okay, which might be in some equivalence class down here. And that would be in the equivalence class that we would call A plus B, because it contains the fraction A plus B over 1, which is the fraction that you would get from the element A plus B, basically. So my assertion is that every element in this domain has an equivalence class that is it, effectively, in this larger mathematical structure. Okay, and the way that you can go from an element in the domain to its equivalence class in this field structure that we've defined is by looking for which equivalence class contains the fraction that element over 1, basically. Okay, so we've now shown that addition within here is exactly the same as it was within the domain, basically. So the structure of the domain is completely mirrored in this bigger structure, basically. Okay, there will be some equivalence classes that are totally new, that don't have any of these fractions, where you just have an element of the domain over 1. But there will be a whole bunch of equivalence classes which will be of this form, the same number as there were elements of the domain, basically. Okay, in addition, multiplication is exactly the same. So in the domain we can multiply A times B to get AB. Okay, in this larger structure what we do is we take our equivalence class, which we are saying is equivalent to A, which has the representative A over 1 in. We take the equivalence class for B, which we're saying has the representative B over 1 in it. We would combine these two representatives to get the fraction A times B over 1. We'd find which equivalence class had that in it, but oh look, that's the equivalence class that corresponded to AB. So my claim is that the structure of this domain is completely mirrored in the structure of this set of equivalence classes, basically. So every element of the domain has a member of this set of equivalence classes which corresponds to it, okay? But there will be some equivalence classes that have no member corresponding to them, basically, and these are the new ones that we've added in. And that when you add any two of these equivalence classes that correspond to the original elements, it's basically an isomorphism to this. Okay, so either you can add them in here and then convert it into the domain structure, i.e. find the equivalence class that corresponds to A plus B, or you can first convert them into here, okay, find the equivalence class that corresponds to A, find the equivalence class that corresponds to B, add those together in this structure, and you'll get another equivalence class, and the answer that you get doesn't depend on whether you do the conversion before the addition or after the addition. So effectively, this structure is within this structure, and we've also shown that it's an isomorphism with respect to multiplication. So basically, this set of equivalence classes that we've constructed, it has a structure that is identical to the domain within it. Okay, so all of these equivalence classes that we can construct from the elements of the domain by saying which equivalence class contains the fraction A over 1, for instance. These equivalence classes they effectively, if we just limited the set down to those equivalence classes and looked at the addition and the multiplication on them, that structure would be isomorphic to the initial domain. But then we've got these new equivalence classes, okay, which do not have a member of the domain which corresponds to them. And these are the new ones, and when you look at this bigger structure then now, the whole thing forms a field basically. And of course I should have two Cayley tables rather than just one. Okay. So that then is how you extend a domain up to have a bigger field, basically. So any domain, any integral domain can be inserted inside a bigger field, basically.